Hello everybody, so this video is going to be on enthalpy and specifically the indirect method, since that's something that a lot of students tend to struggle with. I have an example here from an ACS Olympiad exam. It's not going to be the same exact type of exam, but it's the same type of formatting, and you could at least see the caliber of the questions that they should be asking. So here we have two reactions that we're going to use and manipulate in order to solve the enthalpy change for this reaction down here. And so the first thing that I like to do is I like to look at one of the reactants that we need to find and find it in the two equations above. So we have it on this side. First, we should notice that it's on the wrong side. It's a product when it should be a reactant. And then also we need to notice that there needs to be the same amount of moles. And here it is the same. We have, okay, let me get this to work. We have 1 mole for each. So we don't have to multiply the equation by anything other than a negative sign. Okay, so we need to take this equation and multiply by -1, and that causes the equation to flip. So now our new equation will be P4O6, that's a 4, 6, solid, and that's a reactant, and now P4 plus 3O2 are now our products. And then also we have to look at the value that we have for the change in enthalpy, and we need to switch the sign. So first it was negative, but now that we multiplied it by -1 and flipped the equation, it's now positive. And that should make sense because here it's saying that it releases this much energy per mole when you make this product. But when you multiply it by -1, what it's saying is it takes this much energy to form these products from this reactant. So think about that conceptually so you don't forget what to do when you need to flip the equation. So now we can highlight this new equation and say that we have the right reactant as we have here. Okay? And I'm just going to cross out the top equation now because we don't need it. We don't want any excess clutter. So we no longer need this. So now let's highlight the next one. I'm going to pick a different color. We have 2 moles of oxygen that we need on the reactant side, and let's find that in our top equation. We have 5 moles of oxygen on the reactant side, and then down here we have 3 moles of oxygen on the product side. Now what we can do is we need to subtract. We need to take 5 and subtract from 3. And we have to look at which side that they're on. So a general rule is that whichever side has the higher number of moles is going to be the one where it ends up on. So for example here we have 5 minus 2 and 5 minus 3, and our 2 moles of oxygen is going to remain on the reactant side. Okay, hopefully that made a little bit of sense. But first let's look at our product right here. And where can we find that in the two equations? We have one right here, and we don't have it anywhere else. Now notice that it's 1 mole, same thing as over here, and then it's also on the product side, so everything should be good. So technically, everything should work itself out. When we subtract the 5 minus 3, we get 2 moles of oxygen, and it ends up on the reactant side, which is exactly what we need over here. So since we didn't have to do anything to this value, we just take it as it is. We take this value, and now what do we do to it? We add them up together. So when we add those two numbers, let me just add it up right now so I can give you an answer. You have -2940 plus 1640, and that should give you -1300, and it's going to be in kilojoules per mole. And just to make sure that that is the correct answer, according to the ACS website, it says that the answer is, yes, that is the answer, but it's in scientific notation. They have -1.30 times 10 to the 3 kilojoules per mole. And that's one of the answer choices. So hopefully you can see how this question is organized. One side note is that notice how we subtracted these numbers, we subtracted this number from this number because they're on opposite sides. Now if we had the 3 moles of oxygens on the reactant side, we wouldn't subtract them, we would add them. We would have 5 plus 3 equals 8. But since they're on opposite sides, we subtract them. So that was a simple one. So let's look at a harder one before we move on. So here, I'll try to keep this one a little more organized, but here we have 3 reactions, and we're trying to calculate the change in enthalpy of formation for this reaction. So first, let's start with what we usually do. We look at this reactant, carbon, and we try to find it in the equations above. So I notice that we have one right here, and that is it. I notice that we have twice as many carbons right here that we need, and it's also on the wrong side. So what we need to do is take this equation, and I'll put it in red. Oh my goodness, this is not working. We need to take this equation and divide by 2, so in other words, multiply by half, and also we need to flip it, so we multiply it by negative 1/2. That way we flip the equation and we get rid of the 2. And so our new equation now, it's going to be half of C2H6 gas. Oh, I'm sorry, we have to flip the equation also. Hold on. So that should now be a product instead. So what we actually have is 1 mole of carbon plus 3/2 moles of hydrogen gas. And then now our product, half a mole of C2H6 gas. And so what do we do with the number now? We have to flip the sign, so make it negative, and then 84.7 divided by 2. And we could do that at the end, kilojoules per mole. So that is our new equation. So instead of crossing it out, because I felt like that looked kind of messy last time, let me just delete this and move the new equation. Oh goodness. And move the new equation up there. Hopefully this works a little better. Okay. Because it gets really confusing when you disorganize your equations. That's where you'll make a lot of mistakes. Okay, and just make it a little smaller. So this is the new equation that we're using because we manipulated it in order to get carbon on the reactant side. You notice we have 1 mole of it and it's on the reactant side. So everything should be good there. Now one thing that I'll warn you of is don't mess with the oxygens right now, because if you notice there's fractions involved, and usually fractions get a little messy. We have oxygen on the reactant side and we have 1 mole of it, and here we have half a mole of oxygen. Here we have, I think we had it somewhere else, yes, 7/2 moles of oxygen. So let's just ignore that for now and come back to it, but it can get a little complicated if you address it right away. So let's go to carbon dioxide. So we need it on the product side and we need 1 mole of it, and right now it's on the reactant side and we have 2 moles. So essentially we need to do the same thing that we did to the other equation. We need to divide by 2 and multiply by negative. So we're going to take this and do, oh gosh, okay, we have half of C2H6 gas plus, we have 7/2 times half, oops, so it's going to be 7/4. So make sure you know how to multiply fractions. Sometimes we get lost in the simple stuff. So 7/4 oxygen. Okay, and now we can write our products. We have 1 mole of CO2 since we're dividing it by half, or dividing it by 2, and then 3/2 of water. And then now our enthalpy change is going to be negative 1560.7/2, and let's see, kilojoules per mole. Okay, so Once again, I'm going to erase this one right here, just because we no longer need it, since we already manipulated everything we needed to. Oh no, I'm a little technologically challenged today. Okay. Oh. There we go. I wish my handwriting was a little neater, but it's gonna work out. And then we're gonna put it up here. Okay, so just to make sure that we have everything correctly, we have carbon dioxide on the product side and we have 1 mole of it. So that's great. So now we have to address the oxygens, because at the moment what we have is not gonna work. First, we notice that, let's look at the hydrogen gas. We're trying to get rid of this, correct? And let's see where else we have hydrogen gas. We have it up here. First of all, those don't cancel out. We need to get rid of them because that's not in our final answer. So something's got to change. We have half a mole of C2H6. We have that right here. They're on opposite sides, so they subtract and we can get rid of them. So that's perfect. So we get rid of these. We're trying to get rid of water. So water over here, 3/2 moles, and we have 1 mole over here. So you're starting to notice that since we have to get rid of 3/2 moles of water, and we have 1 mole of water here, what if we just multiplied this by 3/2? Let's try that and see if that's actually something that will work. If we multiply by 3/2, we get 3/2 moles of water, and notice that we can now cancel this one down here. We'll get 3/2 moles of hydrogen gas, and we'll get rid of this one here now because of that. So that actually is working in our favor. And now we'll multiply 3/2 times half, which is 3/4. So let me rewrite it that way. So we have 3/4 moles of oxygen gas. Okay? And now our enthalpy change is going to equal positive 285.8 over, what was it? I'm sorry, times 3/2. It's going to be kilojoules per mole. Okay, so now we no longer need that top equation because we manipulated it. And hopefully this works out. This is actually a question in your workbook, by the way, so you could check if you got the right answer in a certain module. I forget which one. Okay, let's make this smaller. Okay, let's hope that this works out now. So let's highlight the things that we need. We're looking for oxygen. Okay, so this is our oxygen right here. We also have one right here. Okay, so let's subtract those two because they're on opposite sides. Let's see what number we come up with when we subtract them. 7/4 minus 3/4. What does that equal? That equals 4/4, which is also equal to 1. And then since 7/4 is the bigger number and it's on the reactant side, that's where it'll end up. Notice here we have 1 mole of oxygen on the reactant side. So this actually works out perfectly. We also cancel the hydrogen gas because it's right here, and then we can cancel the water. It's on the opposite side. So everything works out, and now all we have to do is just take these numbers and add them all up. I'm not going to do that right now because it takes a little bit of time since we got fractions, but just know that that's the answer that you'll end up coming up with. I don't think there was supposed to be a 1 right here. So just notice that it's going to be 285.8 times 3 divided by 2, and then you're going to add it to whatever this term is, which is negative 84.7 divided by 2, and then you're going to add all that by this term, negative 1560.7 over 2. And once you add those all together, you should get your final answer. It seems like a lot of work, but I think it takes a long time and looks like a lot of work just because I'm having to explain it. But when you do it on your own, it'll not be so bad. Okay? The one major issue with this question was the oxygen. and the fractions. When people see fractions, they freeze. And so you just have to notice what to multiply this whole equation by in order to get the right number to subtract here. Okay. So hopefully that helped you a lot more with enthalpy, and hopefully you don't get a question this hard on your final. Hopefully it'll be more like this first question that we did. I think it was right here, yes. Hopefully it looks a lot more like this because this was a lot simpler. So good luck on your guys' exams.